Hello, I'm Dr. Omaira Ortega, and I am here to talk to you today about some work that I've done over the past year and a half on metamath. I want to thank the organizers at Lathisms, the organizers of this Café con Leche lecture. I have a little café con leche here, just to be in the spirit of things. Sabroso. Okay, so as I said, my name is Omaira Ortega, Associate Professor of Mathematics and Statistics and Assistant Dean of Research and Internships at Sonoma State University, that's in Northern California. And I am going to talk to you today about the mathematics of mathematics, otherwise known as #metamath. I'm going to give you a little introduction into this field, a few examples, and then talk about the work that we've been doing. Okay, so you might have a couple of ideas about what metamath is. It is a term that exists already. However, #metamath is a new term. It's a Slack channel, it's a group of people, it's an idea to organize under. And this hashtag was initially created as a Slack channel, really to organize folks who are participating in the Data Science and Social Justice Long Program at the Institute for Computational and Experimental Research in Mathematics, ICERM, at Brown University in Providence, Rhode Island. And so this work began in the summer of 2022 and continues. So metamath is really just the mathematics of mathematics. It's using math to analyze math. And it builds upon existing work in the science of science, this interdisciplinary movement using the techniques of science to study science. And so this metamath group that I'm part of, we use tools from data science, from mathematics, from statistics to analyze and understand better the mathematics community. And so I want to differentiate metamath from metamathematics, which is an existing branch of mathematical logic. It's a great field. That's not what this is. We're not doing metamathematics. This is metamath. And this hashtag is an organizing space for people to do research, to really just to organize and make the math community more equitable, more diverse, more inclusive. And maybe more importantly, metamath is actually, it falls under the larger umbrella of quantitative justice and promotes social justice. Now, every new research project, every new field comes with both challenges and with opportunities. And so some of the challenges of working in metamath are really just, while there is quite a lot of data out in the world, there isn't necessarily exactly the data that you need in the format that you need all the time. And so in particular, our group that's looking at the mathematical sciences community, there are many questions that we have that we simply just don't have the data to be able to answer those questions. And while it is a challenge, it also presents us with an opportunity to then collect that data or to partner with people who could collect that data for us. Another challenge that we found, it's sort of, well, once you take the time to do this metamath research, you come to great conclusions, you propose solutions and policies that should be put in place. Oftentimes it's difficult to get people to actually take on those policies and implement these policies and these practices. Additionally, the work itself, the research that we're doing isn't always valued as much as other types of mathematical research. And so it's very much, it requires you to convince gatekeepers that this work is valuable, that these results are valuable. You have to convince gatekeepers, and also in some ways you have to become the gatekeepers so that you, or just abolish the gatekeepers, so that this work and similarly, progressive work is accepted and utilized, effectively utilized. Now, I mentioned some challenges and now some more opportunities to doing this work in metamath. Really, 2020 began with a bang, with the global pandemic, the murder of George Floyd. People have had a lot of time to reflect on themselves, to reflect on society, and just the state of the world. And so with that, there's been a huge increase in the attention given to issues in diversity, equity, and inclusion. And in particular, within the mathematics community, there's been a huge increase and focus on DEI efforts. Now, another huge opportunity is there's a ton of data out there, and there has been an uptick in the collection of this data with respect to academia and within academia and about academia. And so that makes even more metamath projects possible because of this uptick in the collection of data. So I want to talk a little bit about the existing work in metamath. Metamath is not a new field. Certainly this metamath phrase that we are organizing under is new, but this work has been going on for quite some time, and so we certainly want to build off of this. I think everyone's aware that women are sorely underrepresented in mathematics, and we know that as people go further and further along in the pipeline, that there are less and less women. So at the bachelor's degree level, women make up a little less than half. Okay, it's still underrepresented even at that level, but a little less than half. And then as you move on, it's closer to 25%, 30% of women, 25%, 30% of doctoral recipients are women. Okay, and then even further along, if we think about, what's the next step after you get your PhD is then getting hired, and 28% of hires at doctoral granting institutions in math were women. Okay, so at each level, as we progress down the career of a mathematician, there are less and less women represented. Now, within mathematics, it's difficult to do scholarly research without funding. It's very difficult to do scholarly research without support and without funding. And so we also looked at some reports from the National Science Foundation, where we see of those proposals submitted to the Mathematics and Physical Sciences Directorate, MPS, that 22% of the PIs identify as women. That's significantly less than half, definitely not parity. Then further, when the NSF looked at their awarded proposals, they found that 26% of the PIs identified as women. Now, when we think also just about tenure track, tenured faculty, in particular at institutions that give PhDs, women only represent 15% of that population. Okay, and so these numbers really just confirm what we already knew. Women are sorely underrepresented, but this is the type of work that has been going on for a while in metamath before #metamath existed. Now, I want to talk about a couple of papers that informed the research that I'm going to talk about from my own research group. So there was a group, these groups are all somewhat related. Each of these papers build on each other, but so Clauset and his group of collaborators looked into faculty hiring, okay? And they demonstrated that there is a hierarchy in faculty hiring. And then Wapman and their group, they expanded on this analysis, and they looked at close to 300,000 faculty in over 10,000 departments at PhD granting institutions specifically. So 368 PhD granting institutions in all academic disciplines between 2011 and 2020. And we actually used their data. And really, they came to the same conclusions. They just had a bigger data set to work from. Then Fitzgerald and their collaborators built on Wapman's paper, really by adding in additional data from the Mathematics Genealogy Project, so that they, one, were only looking at mathematics faculty because it's the Mathematics Genealogy Project, and really looking at who was your thesis advisor. That's part of the information that the data that you get from the Mathematics Genealogy Project, and confirmed that, yes, these hierarchies exist in faculty hiring networks. And it's very much, you can see that there's some schools are more elite than others. Some schools produce more of the PhD faculty than others. Okay, so I want to talk a little bit about the MetaMath team. These are the folks that I've been working with over the past year and a half. And you'll see they come from all over the United States, and they are at different stages in their career, from graduate students, postdocs, early career, mid-career, and more senior. And I really loved working with these folks and getting to know them. I highly suggest working on these teams where just people are at different levels in their career and just bring such a rich perspective. Speaking of perspective, I think it's always important to talk about your own personal positionality in the work that you do. I think especially in mathematics, because we have this belief that mathematics is objective, when in fact, mathematics really is not subjective. There's no way to do research without bringing your personal perspective to that. There's no way to do anything without bringing your personal perspective to it, because you are the individual undertaking that task. And so I think it's important that you know where we are coming from. And so here is a general statement from the whole group, and I'll speak for myself. I'm a non-binary woman, first generation college student. My parents both immigrated to the United States from Panama, and I'm a proud native New Yorker. And I think all of these things really speak to my interest in metamath. You know, I'm Black and Latina or Afro-Latino. And so, you know, that really makes me want to study these types of things. It makes me want to study diversity in mathematics, gender parity in mathematics, racial and ethnic parity in mathematics. And so, and in STEM in general. So, just know that this is my identity really, really pushes me to study these aspects of mathematics very much. And so it's very subjective what I choose to study, but also how I study it. So let's talk about that study. So in our research, we had to use a couple of different data sets. And so I want to share this with you and some of the methods that we use to clean the data, to process the data for analysis. The first data set that we used was this data set from the Wapman group. And so they obtained this data set from the Academic Analytics Research Center out of the University of Southern Florida. And this is a faculty census of just US faculty that they obtained under a data use agreement. There were only tenured and tenure track faculty in this data set, and it was restricted to those employed at PhD granting institutions. And between the years 2011 and 2020. So this would mean, for instance, myself, I'm working at an institution, a California State University institution that gives bachelor's degrees and master's degrees. So I, as a tenured faculty member, would not be included in this study. Additionally, I didn't work here between 2011 and 2020, but just as an example, I want you to understand this is only PhD granting institutions that we're looking at. Now, within this sample, there were approximately 300,000 faculty, 10,000 departments, and 400 PhD granting institutions. So the Wapman group also, this was part of their data, they ranked each of these departments. Okay, and in the Wapman study, they looked across all fields, all of academia, and they created this directed edge graph. Okay, and from this edge graph, they use this spring rank algorithm to rank the departments and rank their prestige. And so they make this assumption that a prestigious department would prefer to hire faculty from other prestigious departments. Okay, and so also this prestige, which we call Wapman prestige, once you apply the spring rank algorithm, it says one university is more prestigious than the other based on their hiring. And so I want to give an example to highlight how this was done. So let's simplify this all the way. We only have two departments, Department A and Department B. Let's say Department A graduates 3 PhDs, and all 3 get hired at another university in Department B. And Department B, they also can award PhDs. They're also a PhD granting institution. They graduate 1 PhD, and that 1 PhD is hired at Department A as faculty. Okay, now because Department A has graduated and then Department B hired 3 of theirs versus the 1 from Department B that was hired at Department A, this implies that Department A has a higher prestige than Department B. Okay, and so that's really how the Wapman prestige works. And this information was included in that data set. And so we'll use this Wapman prestige later in our analysis. Another thing that the Wapman group did was they assigned gender to the faculty members in each of these departments. And they used a supervised learning algorithm to assign this gender. And so when we're looking at the number of faculty members and the percentage of women, keep in mind, in our data set, the units, each observation is a department. Now, another aspect of this Wapman data is that they used a supervised learning algorithm to assign gender. And so they went through and found the names of the faculty members in each department, and then used a machine learning algorithm to then assign gender based on name. Now, as they were doing this, there's going to be some error. For each name, the algorithm assigns a probability that the person is a woman and a probability that the person is a man. There's already some issues with that. We're assuming a gender binary. And certainly they did not go and then confirm with each faculty member, but relied on the results of the algorithm. The Wapman group was trying to be conservative with this algorithm and actually would only use the data if the probability that the assigned gender was correct was 80% or higher. Which is actually a pretty conservative threshold. Now, once gender was assigned, we find that in mathematics, departments overall, these are on average, 16.8% of the faculty members are women. In statistics, 20.9% are women. And in operations research, 19.3% are women. Okay, so again, to remind you, these are just PhD granting institutions. You can see the number of departments in each, and actually mathematics had the most departments out of these 3 fields. But also mathematics has the lowest percentage of women. And so again, these results are not surprising, but they're not good. They don't make you happy to hear. But at the same time, it is very important to know what you're dealing with if you want to make any changes. You need to know that baseline. You need to know the actual reality of your community, of your situation, if you want to make any changes. So we also looked at a data set from the National Science Foundation's Division of Mathematical Sciences, DMS. Okay, and we looked over the same time horizon as the Wapman data, so from 2011 to 2020. We wanted the two data sets to match up, at least in the time horizon. And so the DMS data is aggregated by institution, whereas the Wapman data is aggregated by department. So that was something that we had to finagle. That was some data massaging that we had to do on our side. And in some cases, we had to adjust the institution name ourselves because there were differences between the DMS data set and the Wapman data set, just in the way that the institutions were named, using the in the front or not, ampersand or and, just differences in the way that they were entered. But we needed to make sure that the data could line up. Okay, and then you might also be saying, wait, why are we even looking at this NSF data? For mathematics, DMS is the main funder. And so we figured that because one, it's publicly available data, this NSF DMS data, we can access it. That makes it great. But also because DMS is the biggest funder of researchers in mathematics. Yes, there are other sources of funding, but they are the biggest source. So we focused on this NSF DMS data. Okay, and within this data also, we were able to match 80% of their funding to departments of interest in our analysis, which is great. But where did that other 20% go? The bulk of it, truthfully, went to mathematics institutes like ICERM, where this work was conducted or began at ICERM. But the mathematics institutes receive a big chunk of NSF funding, and we remove them from our analysis because we're looking at PhD granting institutions, not math institutes. They don't give out degrees at math institutes. And so for that reason, we just took them out. Now, the last thing I want to do is just define elite. And so, there's so many definitions for the word elite. And actually, we'll think about this a little bit more towards the end, but the general definition is the part or group having the highest quality or importance. Okay, there's so many different definitions for elite. So in our study, we're actually using the definition that we sort of pulled from the AMS used to do an annual survey where they would define the top quartile, the top 25% of institutions to be the elite. And so we're going to use that. We're just going to say the top 25%. We're going to define that as elite. All right, so now let's talk about some of those results. So just right off the bat, we know the time horizon for the study is 2011 to 2020. What is the fraction of women over this time? The blue at the top is giving you the overall academia results. And so it was just above 30% in 2011, and it's gone up to about 35% in 2020. Now you'll notice there's a big jump between here, statistics in red, operations research in green, and mathematics in orange. And that says a lot about the different disciplines in academia and just the nature of different disciplines and more pointedly, the nature of our fields of mathematics, operation research, and statistics, that all of these three fields that we're focusing on have significantly lower percentages of women in them compared to academia overall. I will also say, on a positive note, all three fields in the mathematical sciences show an increase over this time period. Thank goodness. But I believe we can do better. Okay, so now that definition of elite is going to come into play. Remember, elite is just the top 25%. And we're looking actually at that Wapman prestige ranking that the Wapman group did, using that directed graph. And so here we're just looking at the top 25% according to the Wapman prestige ranking. And now that we've differentiated between elite institutions in our three fields and non-elite institutions in our three fields, just notice that regardless of the field in the mathematical sciences, there's a difference in the percentage of women at elite and non-elite institutions. In fact, there are much less female faculty at elite institutions. Okay. And so I would say, what does that mean exactly? And also, how does that make you feel to know that elite institutions hire less female faculty? Okay, just think about that one for a little bit. Okay, so let's dig in a little bit more. Still separating into the three disciplines, mathematics, statistics, and operations research, so the three disciplines within the mathematical sciences, and comparing that to the percent of women. Now, this is really I'm looking at these graphs because I want to know a little bit more about the nature of these communities. Now, we're all under the umbrella of the mathematical sciences, but within mathematics, within statistics, and within operations research, there are different cultures. Okay, I think it's really interesting when I look at these three graphs, and I hope that you're sort of looking at these and noticing and wondering things. When I look at these three graphs, I look at statistics, and I'm sort of like, well, how is statistics so different from everyone else? You notice sort of in that middle prestige rank, they have the highest percentage of women. In fact, there's this one school over here. Goodness gracious. What's that? In statistics. So I am actually looking at statistics with a little bit of envy. In operations research, it seems pretty flat, this mix here. And then in mathematics, there's this slight trend where the higher the prestige rank, the lower the percentage of women. The lower the prestige rank, the more diversity of percentages of women. Okay, so now we are looking at, I just want to compare this to the one that we were looking at before. So looking at our x-axis and our y-axis, we have percent of women versus prestige rank. And now we want to start looking at that funding, but still comparing it to the prestige rank. Now, in this first graph on the left, we notice that as the prestige rank, as the prestige rank gets better, higher prestige also comes, it appears, with the possibility of more funding. Okay, and then as the prestige rank goes down, you're lower in that prestige ranking, the variance, that spread of funding shrinks down. Okay, there's less funding for less prestigious institutions. Okay, and so at first our group thought, well, we're looking at these raw numbers. Maybe we should instead look at the per capita numbers, looking at, first thinking about, well, how many faculty are even at the school? It could be that, everyone has funding, but there's just, when you get down to these lower prestige rankings, that there's less faculty employed there. And so the graph on the right is looking at that NSF TMS funding still, but now it's per capita. And so when we look at this one, there's some change in the graph, but not really. There's still, the schools with the best funding are those that are more elite. I would say it's even more obvious in this graph. The last thing that we had not compared yet was looking at the percentage of women and comparing that to this NSF TMS funding. Okay, so now that the elite ranking, that the Wapman prestige ranking is no longer on the x-axis. You'll notice just sort of the blue and orange are all mixed together because the blue was the elite and the orange is the non-elite. Now, we notice here still sort of the same business. All the elite schools have low percentages of women. Okay, but now we also have the funding on sort of superimposed on that. Okay, and we looked at this and we thought that, there's more information here. I think that we are missing something. And so we took some time to do a cluster analysis on this to see if there was any natural clustering that this data displayed. Maybe these schools, there's something underlying that we're not seeing that's actually a different type of behavior among these schools. And so when we completed this cluster analysis, there are three distinct clusters. There is the lower right, which are institutions with low NSF DMS funding and high percentage of women. Then in the lower left, we have the red squares with low NSF DMS funding and a high percentage of women. And then the green region with the green triangles is going to be institutions with low percentage of women and high NSF DMS funding. Okay, so there's clearly sort of three different types of institutions in this study. Now, when I look at this graph, the first thing that I see, of course, are these colors, these clusters. But then I think about what's missing. Why are there no institutions in the top right where there are a high percentage of women and high funding? What is it in our mathematical community that makes this so? What is it in society that makes this so? And I also think about, I want us all to dream for a little bit and think about what would it take for there to be even just one institution in that upper right quadrant. What would it take? Yes, and so I really want us to think about this. I think if you've listened to my talk so far, you're clearly interested in this topic. And I believe that you are similar to me and are motivated to actually create institutions that would fill that upper right quadrant there. Okay, and so I also want to highlight some existing schools with high percentages of women. So actually, that's the maximum. The maximum at any institution, at any PhD granting institution, is 50%. And actually, this is between 2011 and 2020, still using that same data set. Bryn Mawr College, Louisiana Tech University, and UC Merced have the highest percentage of women out of any department of mathematics that grants PhDs. Okay, and I applaud these institutions, and I would even say these institutions are truly the elite institutions in mathematics. They're some of the few institutions that have achieved these high percentages of female faculty. And so I would certainly look to these institutions that that are all listed here, all of these institutions as inspiration for how we can fill that upper right-hand quadrant and found, establish, or create these institutions that both have high percentages of female faculty in their math departments and receive a lot of support for their research and activities at their institution. Okay, and so with that, I just want to thank you so much for listening to my talk today. I'm looking forward to the discussion that will follow. Again, I want to thank the organizers at Lathisms for all of the work that they do, and also specifically thank you for organizing this Café con Leche series. Okay, and then just last thing, if any of you want to read any of the papers that are associated with the work that I talked about today, It's all on archive. So again, thank you.